Okay, it's looking like everything's all set up. Happy snow day. So today we're going to be introducing a new idea, a new topic, which is trees. And so I'll start off by introducing a bunch of vocabulary related to that, and then we'll prove a really important theorem. So we're going to give several equivalent characterizations of trees. And that proof is quite involved, but the method is pretty interesting. And the result is super important. It's going to be used just repeatedly throughout the rest of the next couple of lectures. So I'll go ahead and get started. So today's topic is trees. I'm gonna increase the brightness a little bit. Okay. So I'll go ahead and start with just the definition. Just to get us set up with some vocabulary. So a graph with no cycle is called acyclic. And another word for this is a forest. So we'll see this comes up in kind of some different contexts. So a forest is an acyclic graph. Okay, so these two things just mean the same thing. A tree is going to be a connected acyclic graph. Okay, so let me get some pictures going. So for a tree, might have something that looks like this. So we just can't have any cycles in here. And then a forest is, oh, sorry, I forgot to say that this is connected. So a tree is a connected acyclic graph. Okay, so that's crucial. So a tree is a connected acyclic graph, like the picture on the right, and then a forest is just any acyclic graph, so it may not be connected. So we might just have something that looks like a bunch of connected components that are each themselves a tree. So this thing is an example of a forest, and this is a tree. Okay, so some further words related to this. So a leaf is a vertex of degree 1. So for example, these things that I've circled in green are leaves. And in particular, often we will be looking at subgraphs of just an arbitrary graph, which is a vertex, or sorry, which is a tree or a forest. So introduce some words to talk about that. So a spanning subgraph of a graph G. This is just going to be a subgraph whose vertex set is the entire vertex set of G. This is a subgraph with vertex set V of G. And often we'll be interested in spanning trees. So this is going to be kind of the main result of the next couple of lectures. We're building up to something called the matrix tree theorem, which counts the number of spanning trees inside of a graph. So a spanning tree is a subgraph that is a tree, a spanning subgraph that's a tree. Okay, so that's kind of all the definitions. So just to give some examples, so a tree is a connected forest. A forest is a disjoint union of trees. Every component of a forest is a tree. And furthermore, every one of these is bipartite because it has no cycles. So in particular, it has no odd cycles. Okay, so those are trees. And then two types of trees that we're interested in particular. So we've already talked about paths. That's an example of a tree. And then another one that will come up as an example of just some extremal behavior is the star. So this you can think of just as K1 n-1, the complete bipartite graph where you have one vertex in one partite class and then n-1 vertices in the other partite class and all possible edges. So that's the star. Okay, so the first thing that we're going to do quickly is prove a little lemma, and then this will be used in the proof of the theorem that gives us several different equivalent characterizations of trees. So let me give you the lemma. So it says that every tree with at least two vertices has at least two leaves. And furthermore, deleting a leaf from an n-vertex tree produces a tree with n-1 leaves. So this statement smells strongly of induction, so that's kind of where we're headed with this. So let's just prove this lemma. Let's prove the first part first. So in an acyclic graph, an endpoint of a maximal non-trivial path has no neighbors other than its neighbor on the path. Okay, so this is an argument similar to one that we've seen before. So we're going to look at a maximal path and then look at a vertex on the end. If it had a neighbor that was in the path, then that would create a cycle. And since we're working inside of a tree, we have no cycles. If it had a neighbor that was not on the path, then we would be able to make a longer path, which contradicts the maximality. So any vertex in a maximal path has no neighbor other than the neighbor on the path. And so that implies that the endpoints of a maximal non-trivial path are leaves. Okay, and furthermore, why does this path exist? We said that our tree had at least two vertices and it was connected, so there's a path between those two vertices. Okay. So for part 2, we want to prove that deleting a leaf still gives us a tree. So let's let V be a leaf on a tree called G. And let's consider G prime, which will be G, and we'll take out V. Okay, so we want to argue that this is both connected and that it's acyclic. So for connected, let's let U, W be vertices in the graph G that are not the vertex V. So a path from U to V, or sorry, a path from U to W. Okay, so this is a tree, so it's connected. So between every two vertices, we have a path. So the path from U to W does not go through the leaf V. Right, because V has degree 1, and so you would necessarily have to repeat that one edge coming out of V. So this path does not go through V, so it's still a valid path in G prime. So that means that G prime is connected. Okay, then we also want to argue that this is still acyclic. So, but of course, deleting a vertex will not create a cycle. So deleting a vertex does not create a cycle. So we have that G prime is acyclic. And furthermore, we started with n vertices and we deleted one, so we have n minus 1 vertices. So that means that the conclusion holds, so G prime is a tree with n minus 1 vertices. Okay. So that's our lemma. And we're gonna now prove a theorem which will give you an equivalent characterization for trees. And I'll make comments after we prove the theorem about some stuff that's like beyond the scope of this class, but it'll like hint towards some like deeper structure. Okay, so here's the statement of the theorem. So it says the following. For an n vertex graph G, the following are equivalent. Okay, so we're gonna have four conditions. One is that G is a tree, aka connected and no cycles. The second one is just that it has, well, 2 and 3 are one of those conditions together with G having the correct number of edges. So I'll say G, so 2 is G is connected. And has some number of edges. So I'd encourage you to pause the recording and think about what that number should be. I'll fill it in a second. The third one is that G is acyclic and has the right number of edges. Okay, so now I'll reveal what the number is. So the number is n minus 1. And the way that I remember this is to just picture the path. So for example, you could picture the path on 3 vertices that has 2 edges, and the path is a tree. So yeah, this number is n minus 1, and that's how I remember it. And then for u, v, and v of g, so we know that there's supposed to be a path from u to v, but it turns out that this path is actually unique. So there is exactly one path from u to v. Okay, so these are our equivalent conditions. So the way the proof is going to go is we're first going to prove the equivalence of these 3. And actually, so hold on, in my notes, I called them A, B, C, D. So I'm going to switch this up because otherwise I'll forget to translate. Okay, so we're going to prove the equivalence of A, B, and C. And basically how we'll do this is we're going to start with A implies BC. And then next prove that B implies A and C, and then prove that C implies A and B. And then lastly, we'll prove that A and D are equivalent. And so that will give us the full thing. Okay, so this is a lot because there's 5 parts to this proof, but they are all separately kind of interesting arguments. So yeah, so let's go ahead and do this, and it will use all of the properties. It's a very satisfying proof. Like, it uses all of the properties in exactly the right ways, and it's very clever. So okay, so let's see the proof. Okay, so to start off, we're gonna do A implies B, C. Okay, so what is necessary for this? We're gonna assume connected and acyclic. So then to prove either B or C, the only remaining thing is to show that it has n minus 1 edges because we already assumed connected / acyclic. Okay, so our assumption implies the first part in both cases, so all that's left is to show that we have n-1 edges. So for this, we need to assume connected and acyclic. And prove that it has n-1 edges. And that is the content of this proof. Okay, so we're gonna go for this part by induction on n, the number of vertices. Of the graph G. Okay, so for the base case, we'll look at n equals 1. And in this case, if the graph is acyclic, then, and it has one vertex, then that means that it has no edges. So acyclic and on one vertex implies 0 edges. And in this case, 0 is n-1, so we're good. Okay, so for n greater than 1, we're gonna suppose the implication holds for graphs with fewer than n vertices. So just assume the inductive hypothesis, and then given that G is acyclic and connected by the lemma, we have a leaf V, and G prime, which I'll say is G minus that leaf, is also a tree. And G prime is on fewer than n vertices. It's on n-1 vertices. So by the induction hypothesis, G prime has n-2 edges, because G prime had n-1 vertices, so it has one fewer edge. And so how did we get from G prime to, sorry, from G to G prime? We deleted one vertex and one edge. So that means that G has so that means that G has, maybe I can just get rid of this altogether. Oh my God. Okay, there we go. So G has n-1 edges. Okay, so that finishes that part of the proof. So if we're connected and acyclic, then we have this little induction argument that shows that you have the right number of edges. Okay, so the other proofs are a little bit trickier. So let's go through this. So for B implies A comma C, so let's go back to the statement. So we're assuming connected and n-1 edges. Okay, so that for each of B and C implies already we're good on connected, we're good on n-1 edges, but we need to prove acyclic. Okay, so for this part, we are assume connected and n-1 edges. And we're going to prove acyclic. Okay, so let's suppose G is connected and has n-1 edges. Then we're gonna delete edges from cycles in G. So we don't know if it's acyclic or not, but if it does have a cycle, then delete an edge and continue doing that one by one until the graph is acyclic. So we're going to delete edges from cycles in G one by one until the resulting graph G prime is acyclic. Okay. Okay, so I want to argue that G prime is a tree. So we already know that G prime is acyclic. And furthermore, since no edge of a cycle is a cut edge, and we're only ever removing edges that were in cycles, G prime has to be connected. So since no edge of a cycle is a cut edge, so as a reminder, a cut edge would increase the number of connected components if you delete that edge. So no edge of a cycle is a cut edge. So, oops, that doesn't grammar. G prime is connected. Okay, so now we know G prime is connected and acyclic. So G prime is a tree. And we've already proved that trees have n-1 edges. So G prime has n-1 edges by what we've already proved. And thus, we in fact, so we started with a graph G that had n-1 edges, and we deleted some edges and then arrived at G prime, which also had n-1 edges. So that means that in fact, we deleted no edges. So thus, we must have that G prime is equal to G, and that means that G is acyclic. Okay, I'm gonna pause there. I love this little argument. I think it's like so clever to just get yourself back to being a tree and then use the part that we already proved to um assert that actually you did nothing. Okay, so now we're gonna do C implies A and B. Okay, so let's go back to the top. So now we're assuming acyclic and n-1 edges, and we're gonna prove A and B. So we're already good on n-1 edges, and we're already good on acyclic. So that means that we need to prove connected to get both parts. Okay, so we're gonna assume acyclic and n-1 vertices. And then we're gonna prove that it's connected. Okay, so let's start by giving names to the connected components of C. So I'm gonna of G. So I'm gonna let G1 up to GK be the connected components of G. Okay, so since G has no cycles, each component has no cycles and is connected, so it's a tree. So since G is acyclic, each G sub I is acyclic and connected. So each G sub I is a tree. Oops, and I wrote, sorry, in this assumption I wrote vertices and it should be edges. Okay, so each G sub I is a tree. So thus, again, by the part of the theorem that we've already proved, each G sub I has the correct number of edges. So this implies that the number of edges in G sub I is equal to the number of vertices in G sub I minus 1. Okay, so basically now what we're going to do is count the number of edges in the graph G by adding up all the edges in each component. So let me write this. So we're going to count the number of edges in G. On the one hand, by the assumption, we know that this is equal to n minus 1. So this is by assumption. But then we also know that G consists of these components. There's K of them. And so maybe I'll write this in more steps. So every edge is contained in some component. So we have this equality. And then we also know that the number of edges in each component is given by this equation. So this equality. Okay, and then this comes out to n minus k. Okay, so why is that? So from this part, so we're counting up the number of vertices in each component. Every vertex of G is contained in some component. So if we sum over all components, the number of vertices, then we just end up with the number of vertices in the graph G, which is n. Okay, and then furthermore, for each component, we're subtracting 1, and we have k components, so we get a minus k. Okay, but now looking at this equality overall, we have that n minus 1 is equal to n minus k, and so that implies that k is equal to 1, and so G must be connected because k was the number of connected components of G. Okay, so that finishes that portion of the proof. So now we're gonna prove the equivalence of A and D, that last part. And I'm just gonna start a new page. Okay, so we have A implies D. So let's go back. Okay, so we're gonna now assume that G is a tree, which by what we've already proved also means that it has n-1 edges. And then we need to prove that there is a unique path from U to V. Okay. So let's prove that A implies D. So maybe I'll write what we're assuming. G is a tree, which we now know some things about what that means, and prove unique path. So since G is connected, every pair of vertices is connected by a path. So we know that there exists at least one path between every pair of vertices. So since G is connected, there is at least one path between each pair of vertices. Okay, so now I'm gonna choose a pair of paths PQ that are distinct from one another with the same endpoints such that the total length of the two paths is minimal among all such possible choices, such that, let me write. So we're gonna say the number of edges in P plus the number of edges in Q. We want this quantity to be minimal among all possible choices. So this is like towards a contradiction. We're assuming that there are distinct paths between some pair of vertices, making a minimal such choice, and then we will get a contradiction out of this. So by this extremal choice, no internal vertex of PQ can belong to the other path. So this is my claim. So by the extremal choice, no internal vertex of PQ can belong to the other path. And here's a picture. So, okay, let's say here's the vertices that the paths are going between, and here's some other vertices. And let's say they both go through this vertex in the middle. Okay, so this is like P, and I'll write Q in green. Okay, so if they both share an internal vertex, then there is a shorter pair of paths with the same endpoints, namely like this pair of paths with those endpoints, or this pair of paths with these two endpoints, right? So because of this minimality, this situation cannot happen. So they don't share any internal vertices. And this implies that P union Q is a cycle. which is a contradiction. Because we assumed that we had a tree which is acyclic. Okay, so it is not possible. Okay, so let's like recap. We know that there is at least one path between every pair of vertices. Furthermore, we argued that there cannot be more than one path between every pair of vertices. And so that means that we do have exactly one path between every pair of vertices. So that finishes this part of the proof. Okay, then one last bit that we need to prove is that D implies A. So we're going to assume unique paths. And I'm going to also add there exists, because we're saying there's exactly one path between every pair of vertices. And we want to prove that it's a tree, so it's connected and has no cycle. Okay, so here's how the argument goes. So connected is very easy. So it's connected because there is a path between every pair of vertices. And let's give a quick argument as to why it's acyclic. So if there was a cycle, there would be two paths between some pair of vertices. So if there was a cycle, there would be two paths between some pair of vertices, which is a contradiction. And so that means that there is no cycle. Okay, so that finishes the proof. So let's go back to the statement. So I would encourage you to just internalize the statement of this theorem, because as it comes up in the next couple of lectures, we're going to use these equivalences more or less freely, and we're not really going to stop and say necessarily that like this is because of this theorem. Like it's you go back and forth between these so often, these properties so often, that this is now just like kind of assumed knowledge. Okay, so now I'll make some comments. Yeah, let me copy this. Copy A, B, and C. Okay. So I'll make some side remarks. This is like not this is not relevant to the course material, but I just want to make some comments about like how does this fit into math that you've done previously and math that you might do in the future. So here's this theorem that we just proved. So these three things are equivalent. And in linear algebra, you had kind of a similar theorem. So you had, I'd say part A is, this is like conditions for a set of vectors to be a basis. So let's call this set. So let's let S be a set of vectors. So the following are equivalent. S is linearly independent and spanning. And I'm going to change so S is spanning, comma, linearly independent. B, S is spanning, and has n vectors. And C, S is linearly independent and has n vectors. Where n is equal to, in this case, the dimension of the vector space that they came from. So these two theorems look very similar. And you might be wondering if there's some sort of underlying structure that connects these two statements. And that underlying structure is matroids. So matroids give a generalization of both graphs and vector spaces. And yeah, so this theorem is something that's like true more generally for matroids. Matroids are some combinatorial gadget that mimics the behavior of both of these objects. And this is something that you may learn about if you go on to take more discrete math or combinatorics courses. And then like a further comment along these lines is in the book Proposition 2.1.6, which I'm not going to prove now. This is what's known as the basis exchange property. For matroids. So when I look at Proposition 2.1.6, in my mind, the content is that this is proving that graphs are matroids. So that's like my take on this thing. So if you're interested in this, you could look up Proposition 2.1.6 in the book and look into some stuff about matroids, and you can also feel free to ask me more questions about it in office hours or wherever. Okay, so I'm going to give you a corollary of the theorem. And I want you to pause and think about why each of these statements is true, because I'm not going to prove it. So every edge, first part, every edge of a tree is a cut edge. Okay, part two, adding one edge to a tree forms exactly one cycle. And then the last thing is that every connected graph contains a spanning tree. So go ahead and pause and justify these statements to yourself. They all follow from things that we've already proved in a relatively straightforward way. Okay. So now, slightly shifting gears, I'm going to talk about distance in trees and graphs. So where we're headed right now is I'm going to talk about this stuff kind of related to distance for the rest of this lecture. And then next lecture, we're going to start with spanning trees and enumeration. And we'll see two major theorems. One, just we'll get to next lecture. It's called Cayley's formula, and it counts the number of trees on a fixed vertex set. And then we'll start setting up for the matrix tree theorem in the next lecture, and then in the following lecture, we'll prove the matrix tree theorem, which is like, I think the matrix tree theorem is like one of the coolest theorems that you encounter in this course, definitely. And like in my undergrad, it was my favorite theorem that I saw the whole time. So I'm excited for matrix tree theorem. That'll probably be next Tuesday. Okay, so going back to distance. So distance is an idea that you're frequently interested in applications. Like you might want to know, for example, like if I want to fly between two cities, how many flights does it take? Or it's easy to imagine a lot of different scenarios where you want to know the distance, or you want to try and minimize the distance. So this is like something we're gonna study now. So let's make a definition. So if a graph G has a path between two vertices, then the distance from U to V, which is written as d sub G of UV, when we need to remember what graph it is, or if there's no confusion, we could just drop the G and write d of UV. Okay, so it just depends on the context. Like sometimes in our proofs, we're dealing with more than one graph, and then you need to specify what graph you're thinking of. But if it's clear from context what the graph is, then you can just write DUV. Okay, this is the minimum length of a UV path. Okay, so it's the number of edges in that path. And if there's no such path, then you say that the distance is infinity. I think this is just a convention. And then the diameter of G is the maximum over all pairs U and V of the distance from U to V. Okay, so what is the greatest distance that you might have to travel inside of this graph? Okay. So let's look at the following example. I'm going to ask you, what is the diameter of the following graphs? So the first one will be the Peterson graph. I'll draw that again because it was a while ago that since we last saw it. Okay, so what's the diameter of that graph? What is the diameter of the cycle C sub n, the cycle with n vertices? And what's the diameter of a tree? You can just describe what the diameter is of any tree. Okay, so pause and think about what the diameters of these should be. Okay, and then I'll give you the following question. So how does the diameter of a graph relate to the diameter of its complement? So why should these two things be related? Well, if you have a large diameter, that means that you're missing a lot of edges, right? There's two vertices that are very far apart. There's no faster way to get between them. So that means that you're just lacking edges, kind of just like heuristically. There's not very many edges. But then that means that the complement has a ton of edges. And so the diameter will be small. So again, I would encourage you to work out a couple of examples. Work out some examples and try to guess a relationship. And like make a conjecture about what this should be. So if you want to explore this, then pause now and do that because I'm about to reveal what the theorem statement actually is. And so yeah, so pause if you want to explore this a little bit before I reveal the answer. So the theorem is that if G is a simple graph, then the diameter of G is greater than or equal to 3 implies that the diameter of G bar is less than or equal to 3. Okay, so that's the statement of the theorem. I'll go ahead and prove it. Okay, so what does it mean for G to have diameter greater than or equal to 3? So since the diameter is in particular strictly larger than 2, there exist non-adjacent vertices with no common neighbor. Okay, so if every pair of vertices U and V had some common neighbor, then that would mean that between every pair of vertices, there's a path of length 2, and so the diameter would be 2. But in this case, the diameter is greater than or equal to 3, so that means that there has to exist vertices satisfying this. So they're non-adjacent and they have no common neighbor. Okay. So that means, I'm just going to rephrase that observation. So every X in the vertex set minus UV, so every other vertex, has at least one of U or V as a non-neighbor, right? Because if it had both of them as a neighbor, then U and V would have a common neighbor. Okay, so let me get a little picture going. So here's our vertex U and our vertex V. So every other vertex in the graph, which I'll just draw them all up here, is either it's in one of two categories. So it's either, or one of three categories actually. So it's either a non-neighbor of U, it's a non-neighbor of V, or it's a non-neighbor of both. It's not possible for it to be a neighbor of both of these vertices. Okay, so these clouds are meant to indicate like non-neighborness. So like this vertex could be connected to V. These ones could be connected to U. The ones in the middle are not connected to either, and then these things could be connected to each other in some way. Okay, so that's our picture. So in this statement, like all of these guys are the X's. Okay, so what's happening in G bar? So in G bar, so the complementary statement is that every one of these X's is adjacent to at least one of U or V. Okay, so let me draw the complementary picture. So this is our G picture, and on the right, I'll draw our G bar picture. Okay, so we've got U and V, who are now connected because we're in G bar. And we have the vertices that are not U or V up here. Okay, so now the blue cloud, did I draw enough of these? Yeah, okay, so the blue cloud, now all of those vertices are going to be connected to U. Okay, so that was our blue cloud. In G bar, these are now all connected. And then in our pink cloud, those are all going to be connected to V. And then, yeah, whatever, there's going to be more edges up here, and I'm not going to draw them all because I don't care. So more edges. Okay. So then, since we also have UV in the edge set of G bar, we have that for every pair of vertices xy there is a path in G bar of length at most 3. Okay, so why is that? We already know that every vertex up here is connected to at least one of U or V. And same thing for every vertex here. So how do we get from one vertex to the other? We go to the guy U or V that it's connected to. Potentially we need to pass over to V, and then we go to the other vertex. Okay, so that path has at length at most 3. We may not even need to, right? So if I pick 2 vertices just from the blue cloud, there will be a path of length 2. If I'm going from blue to red, then I will need a longer path. But we know that in any case, there is a path of length at most 3. So that means that the diameter of G bar is at most 3. And that finishes the proof. Okay, and I'll mention one more kind of like application E type concept / result that's in this section, just to wrap things up. So in, say, a communication network or like a travel network, like I was giving an example with the airplanes, a large diameter could be okay as long as for most pairs you can communicate via short paths. So maybe there's like 2 vertices are very far apart, but on average, there is a short path. So we may want to study instead the average distance. So we may want to study so this would be summing over all pairs U and V of vertices in the graph of the distance from U to V, and then dividing out by the total number of possible edges, which would be n choose 2, but it's equivalent to just not divide by n choose 2. So we're just going to study this number, which I'll call large D of G. And this is called the Wiener index. Okay, so this tells you something about the average distance in a graph. And there was kind of an interesting paragraph in the textbook about how, and I don't know anything about this, but how properties of chemical compounds actually have to do with their Wiener index. So this apparently is actually something that scientists are interested in. So so here's a theorem that gives kind of like an extremal type of flavor statement about the Wiener index, which is it says the following. So we're going to look at the possible Wiener index among trees, and then I'll give a statement for general graphs. So among trees with n vertices, the Wiener index is uniquely minimized by, okay, which type of tree? I'll give you a minute to think about what tree should go there. And uniquely maximized by what other type of tree? Okay, so pause and think about what should go in the blanks. And now I'm going to fill them in. So it's minimized by stars and maximized by paths. Okay, so I'm not going to prove this, but what I would encourage you to do as an exercise right now is to calculate d of the star, which is k1 n minus 1, and d p sub n. Okay, so let me give you some hints for this because it's a little bit tricky, but it's like a fun calculation to do. Okay, so this one, the star is more straightforward. I think you can just do that. And then my hint for computing dpn is to do a recursion. And then you're also going to need induction and a binomial identity called Pascal's formula. Okay, so this is like a really fun calculation to do. So I would definitely encourage you to do this. And maybe I'll tell you, actually, yeah, I'll tell you what the answer is in both cases so you know what you're working towards. So for dkn, or sorry, dk1 n minus 1 the star, this is equal to n minus 1 squared, and this one is equal to n plus 1 choose 3. Okay, so I would encourage you to work that out. And then the last thing that I'll say is, so this theorem is just among trees, but then in general, over all graphs, obviously it's minimized by the complete graph. Maybe I'll write this out. So over all graphs, this is minimized by the complete graph Kn. So maybe you could also calculate dKn. And then it is still maximized by the path. It's fine. Okay, so I'm gonna stop there for today. And when we pick up tomorrow or on Thursday, we will be talking about enumerating spanning trees, so Cayley's formula, and we'll be working towards the matrix tree theorem, which is my favorite theorem. Okay, so I hope you're all enjoying your snow day, and I'll see you on Thursday.